Alright, welcome to part 3 of our video lecture on Chapter 8. We've got 3 different, none's better than the other, well, 3 ways to notate a subnet mask. We can do it in binary, we can do it in decimal, which most people are familiar with because when you do an IP config, you see your subnet mask in decimal. Or network engineers are cooler than that, and we use a slash notation. So slash and then the number of bits that belongs to the network. So a /12 means that there's 12 bits for the network. Some more examples. 8 ones, 8 ones, 8 zeros, 8 zeros in binary is exactly the same thing as saying 255, 255, 00 in dotted decimal, which is exactly the same thing as a /16 network. One more example. 8 ones, 8 ones, 8 ones, 8 zeros in binary is exactly the same. So all of this belongs to the network. These are all the network bits. And this is how many bits you have available, 8 bits for your hosts. So a very small network. In dotted decimal is our good old, what you probably use at home, 255, 255, 2550. Network engineers are lazy. For the same reason we don't like saying www. We don't like saying 255, 255, 255. It's easier to go /24. Exactly the same thing. Okay, before we leave this section of how you calculate a subnet mask, we need to talk about what some typical subnet masks are. Your public... On the public side, your IP address and your subnet mask will be assigned to you by your ISP, and there's nothing you can do about it. Right? They'll assign you a public address and a subnet mask, and the subnet mask tells you how many hosts you can have. So maybe you're buying, one address, maybe you're getting 16 addresses, maybe you need 24 addresses, maybe you need hundreds of addresses. The subnet mask would change, but they are going to assign that to you. It's just on the private side where you've got some choice in the matter on what subnet mask you use. I would put it to you that if you have a choice, you will always choose a Class A. Now, Class A means you've got 8 bits for the host, and the rest of the bits for sorry. Let me back up. Sometimes my mouth starts going too fast. A Class A private IP address range means you have 8 bits for the network, and the only range you can use is the decimal number 10. That's reserved for private address space, which means you're never going to conflict with anything on the internet as long as you use a 10net /8, which means you've got 3 octets to use for your private address space, which gives you the most flexibility. I would recommend you use this even if you're starting a very small mom and pop network. Don't use a 192.168, which comes default on any Linksys piece of crap device, right? Switch over and go ahead and use a 10net network. Now you can't mix and match. You can't use a 10net with a 255, 255, 255 subnet mask. It's got to be a /8. This is what I've done at every organization that I've been a part of, and we've had to go through some migrations at some of them to change from a smaller address range to a bigger address range. It's better if you start off with the biggest address range. So just use this. When in doubt, use a Class A. Class B is a weird address space. Some students like it. I don't know why. It's just weird to me. It's originally Class A was designed for large networks. Class B, medium size. Class C, small size. It's more complicated than that. Using 12 bits for the network is what the RFC says. Now, typically, what you're going to see in the real world is the first 2 octets used for the subnet mask. Same thing with a Class C. For years I thought that it was supposed to be a /24, but apparently you've got 16 bits that you can use in a Class C private address space. But more typically what you see is a 255.255.255, which is a /24, not a /16. So according to the RFC and the textbook, this is correct. Let's say this is correct for a Class B. I'm just telling you, in the real world, what you're going to see is this. Now, on the exam, what I'm going to do is say a Class A is most typically, which of the following address ranges. A Class B is typically what address. A Class C is typically what address. When I say address, I mean subnet mask. The reason you want to use a Class A, this 10 net space with just 8 bits for the network, means you can do some clever things. You can make the dots a little more meaningful. So for example, 10, can't do anything with that. 1, it's very nice to make that your location. Number 1 is corporate. Number 2 is sales. Number 3 is R&D. Number 4 is manufacturing. Number 5 is the Japan location. Number 6 is Germany. Number 7, it can be by location. And the third one can be the type of device it is. Maybe 1 means a router, 2 means a switch, 3 means an access point, 4 means a printer, 5 is something else. It's good if you use a meaningful logical system for assigning IP addresses, and then the last octet obviously for assigning to individual hosts. That's a way I've used that it never fails. I've never had it not work out to do that, to use each octet to mean something, just so when you're looking at an IP address, you know exactly where it is and what device that is, as if by magic. That's why network engineering is cool. So that's what I mean by sensible or logical addressing. Just give it some thought. If you have a choice, use this one. Now, classful versus classless. Classful means that the subnet mask is going to end at a decimal. Classless addressing is going to steal some bits from one side or the other. So maybe if I give you an example, if I look at my IP addresses that are, this is an old screenshot, but assigned to my Ethernet adapter and then my wireless adapter, notice I've got 2 network cards in my laptop. The Wi-Fi, for whatever reason, is using what I would call a Class C subnet mask. Well, let's just call it a /24. Also notice that we're using public, not private addresses on the inside of our network. That's weird. That's just because we're a state of Illinois public institution and we got assigned a buttload of public IP addresses early on because we're an educational institution. You will never see this in the real world. No, this should always be a 10 number on the private side. But we're different. We're SIUE. Just notice that the subnet mask is a /24, which is very typical. Notice that up here it's 255.255. What? 252? That means we're using fewer bits for the network so that we can have more bits for hosts. Usually there are very specific business reasons. There's a business logic for setting it up this way. This is an advanced topic. It gets confusing. But if you see a weird subnet mask where it's not a 255 or a 0, it's some other number, they're doing classless addressing. Like I said, I've lived through at least twice 2 big projects where we had to renumber every freaking device on the network. I mean, thousands of hosts to switch from a 192 address scheme, just from lack of foresight, to a 10-net address scheme for our private IP address range. So there are 3 that you're allowed. The 192, the 170, 172.16, whatever, and the 10-net. On the private side, always use the 10-net so that this is not you in the future. I want to save you some pain. A special IP address is 127.0.0.1. This won't be on my exam, but it might be on a Network Plus certification exam and certainly on a Cisco CCNA exam. knowing that 127.0.0.1 is your loopback address, i.e. yourself, i.e. your home address. So it's an address you can use for testing purposes. Even if you don't have a legitimate IP address assigned to you, say DHCP is failing, you can always ping 127.0.0.1. Try it right now. Here, let's just do it. 127.0.0.1. Ping 127.0.0.1. Ta-da! See, works every time. If this ever does not work, your TCP/IP stack is corrupted, and you've got to reinstall some software at that point. Ugh. I may have mentioned this before in class, but it's important to repeat. If you ever see an IP address, if you do an IP config and you see 169.anything, 169.anything, that's a bozo address. It's a placeholder address. What's happened is Windows tried to request a DHCP address. It could not get one, and in order to boot, it's got to have an IP address. So it gives itself a dummy address, which is this 169 address. So don't ever use this address. You never want to see an address that starts at 169. If you do, you've got to somehow, well, you can reboot to get DHCP to send a new request, or you can do an IP config /renew or /release and then /renew to get a new IP address. But this means you don't have a valid IP address. All right. So far, we've been talking about IPv4 addresses, good old-fashioned 32-bit addresses. When a packet arrives at a router, how does it know? How does it know that it's IPv4, IPv6? Well, first of all, that router has to have both protocols installed, both version 4 and version 6, in order to recognize the difference. But it can tell based on the very first bit value of the incoming packet. If it's a binary value of 4, then it's version 4. And again, the only fields, even though this chapter gets heavy duty into all the fields of an IP packet, I just want you to know the source and destination address fields that are 32 bits long in an IP packet. But based on that, let's look at some differences with IPv6. So same thing when an IPv6 packet comes in, it's going to, let me see if I can, well, similarly in an IPv6 packet, this very first bit is going to have a value of 6 instead of 4, and that's what tells the router to process that packet as a v6, version 6 IP packet. So there's some big differences between version 4 and version 6. The biggest difference is just the number of addresses, the address space, the range of possible addresses we can use, the number of mathematical alternatives we can use, because it's 2 to the 128 instead of 2 to the 32. Instead of giving us 4 billion addresses, which we ran out of years ago, we have 340 undecillion addresses, which is going to last us for quite a while and even accommodate all the Internet of Things for quite some time. Graph. Notice that IPv6 is not 100% of Internet traffic. It's still a small percentage just because there's so many ISPs that have not converted. A lot have, the big ones have, the smaller ones not necessarily. Just FYI, you get your IP addresses assigned by your ISP. Where does the ISP go to get their IP addresses assigned? They go to ARIN.net, so in the US. There are several registries, but we go to the American Registry for Internet Numbers. FYI. The next big change with IP version 6 is that in order to accommodate this address space and to keep if we kept decimal, it'd be just an incredibly long address. So in order to kind of compress things, we use hexadecimal instead. So you can see how long an address is in binary. In hexadecimal, we're able to shorten it because we have 16 options per character here. And if IPv6 addresses look a lot like MAC addresses now, yeah, because they're both written in hexadecimal. Now, because we're lazy, and for the same reason we don't like saying www, and we don't like saying 255.255.255, we don't like saying 000000000. So if there are a bunch of leading zeros, you can actually drop the leading zeros. And consecutive dropped zeros can be dropped further into just being represented by 2 colons. What's interesting about these addresses, the new notation, even though it looks bizarre to me, an old-timer, it looks bizarre, you can still ping them, just like you do a decimal address. Just like you would do a ping 192.168. whatever. You can put ping in front of this address and it'll give you replies, which is pretty cool. So I put all the kind of rules for how we notate IPv6 on one slide, just a quick summary. And the picture I wanted to show you before, where the first bit has a value of 6 that tells the router that this is a version 6 packet. So just remember that version 6 addresses are 120 bits long, so the source and destination addresses are 2 fields, the 2 important fields I want you to know in version 6, 128 bits long. Now you might be asking yourself at this point a very important question. Uncle Tim, if IPv6 addresses are written in hex, how do we notate subnet masks? Not subnet masks. Private address space in IPv6. How do we figure out what a legal private address is? So the 3 legal private address spaces are 10net, 172.16, and 192.168. So the question you should be asking yourself is, what's the equivalent in IPv6? I'll tell you, they actually made it a lot easier in IPv6. FDD, FD, FDD, anything that starts with FDD is the private address space. They don't call it private addressing, they call it EULA, unique local addressing, which is stupid. But any address that starts with FD is going to be private address space, and again, you can't conflict with anything that's on the internet. Also, what's wacky with IPv6 is we may not need NAT. There's an argument, a big argument on the internet, that we don't need NAT because there are how many addresses? 340 undecillion addresses. Why do we need to translate addresses? Just makes things more complicated. I like NAT because I think it gives an added layer of security from hackers just by changing the IP address range. You're making it a little harder for them, but this is an ongoing debate